Hey guys, in this problem we're looking to find the altitude above the surface of Earth that a geostationary satellite must be in order to maintain a stable orbit. In doing so, it must travel at an orbital velocity of 3,070 meters per second. And at this altitude and that speed, it will move around the Earth one time every 24 hours, so it remains stationary in our night sky. Let's start this problem by setting up and drawing a picture. So we have Earth, and Earth has its own radius. Call that RE. And out far away, we have our satellite. There's my satellite. And it's following an orbit around the Earth. And it is some altitude, which we're trying to determine above the surface of the Earth. Now, in most of these problems where we're dealing with the universal gravitation formula, we're really looking for the total distance to the center of the Earth, which I've called d in most of our equations. Again, if you look online, you might see it termed as r, but I find that this might be a little bit less confusing to use the letter d. So in this problem, this satellite is whizzing around with a velocity of 3,070 meters per second. And they give us a time increment. This is the time to travel around one complete rotation. This is also known as the period, which we use the letter T, capital T, to represent the period, and that is 24 hours per rotation, which, like everything else, we'll convert to seconds to make sure we're in MKS, so all of our units work out in the problems. So I'm going to set up a fence post. I want to cancel hours by putting it in the denominator, and I want to go to seconds. And there are 3,600 seconds in 1 hour. And so I can multiply in my calculator 24 times 3,600. As we expect, there's a lot of seconds in an hour. In 24 hours, 86,400 seconds. So that's the time for it to travel that distance. There's actually two ways to solve this problem. The first doesn't require us to even use our universal gravitation formula. We know the velocity of the satellite. We know the time it takes to go around the circle. And if we can find d, then we can figure out the circumference of the circle. So in doing option 1, we're going to actually use the time given to solve the problem. And we know that it travels a total distance which is equal to the circumference. So we'll call that x. That's the distance around the circle, which is the circumference, which would be 2 pi times the radius of the circle, which happens to be, in this case, d. We know the velocity, again, is 3,070 meters per second, and we know the time it takes to make that trip is 86,400 seconds. And as we saw earlier in the year, we know how those variables relate. Velocity is distance over time, meters per second. And so we can plug in the variables we have. 3,070 equals 2 pi d, which is the distance it would take to go around the circumference of the circle, over the time, 86,400. And now we just need to solve for d. So I'm going to multiply both sides by 86,400. I have 3070 times 86400. So now I've got 2 pi d on the right side, and so I'll need to divide by 2 pi to isolate the d. Now be careful, make sure you put parentheses, because if you don't, your calculator will divide everything by 2 and then multiply by pi. We want to divide the whole thing by 2 pi to get a distance that is 4.22 times 10 to the 7th meters. The distance to the center of the Earth is 4.22 times 10 to the 7 meters. However, if you look at the problem, they're not asking for the distance to the center of the Earth. They want the altitude. And the distance is equal to the radius of the Earth plus the altitude. So therefore, the altitude would be the distance minus the radius of the Earth. And the radius of the Earth is 6.38 times 10 to the 6 meters. And so I can use that formula. Altitude would be the radius of the Earth minus the distance minus the radius of the Earth. Which would be 4.22 times 10 to the 7 meters minus 6.38 times 10 to the 6 meters. So my calculator, I've already got this value in there. I don't want to retype it. So if I just put minus, it'll take that previous answer. And I'm going to subtract the radius of the Earth. You might have it stored in as R already. I'll just type it in, 6.38. Second e to the 6. And there's my answer. It looks like the decimal place we need to move 7 places to get between the 3 and the 5. We'll write it in scientific notation. 3.58 times 10 to the 7. Above the surface, 3.58 times 10 to the 7 meters. Pretty far up. Now let's look at option number 2. Now this satellite is in stable orbit. And because it's in an orbit, it's moving in a circle. And anything moving in a circle must have a centripetal directed force towards the center of that circle, which, as we would imagine, the only force we have here is gravity, which is acting towards the center. And that's causing a centripetal acceleration, AC. So in order for it to be in orbit in a perfect circle, we know that the centripetal acceleration has to equal gravitational acceleration. And we have an equation for AC. That's just velocity, tangential velocity squared. The distance to the center of the circle, we have R. And AG for any object is just G. It's the mass of the object causing the gravitational field over the distance to the center of that object squared. And remember, R is the same as D. R is a distance to the center of the circle. And so I can replace R with D. I'm going to get V squared over D equals G. In this case, the object we're orbiting is actually the mass of the Earth. We'll plug that in. V squared here. I can cancel out one of these here. And I actually want to solve for D. So I can do a little algebra right now. I can multiply both sides by D and divide by V squared. If we talked about in class, you really can just flip-flop the V squared and the D. And I get an equation that says the distance to the center is G times the mass of the Earth over the velocity squared. And I can plug in my numbers. G is 7 times 10 to the negative 11. The mass of the Earth is 5.98 times 10 to the 24th. And that velocity we got, given in the problem, is 37 meters per second, and that is squared. So my calculator, if you stored G, which I have as the correct value, I've actually stored the mass of the Earth M. There it is. So all I need to do is do alpha G, alpha M, and divide by 3070 squared. And I get the same number I got before, 4.2. It's rounded a little bit because of the values we're using for Earth. Might be slightly different. But I get 4.23 in this case times 10 to the 7 meters. And when I subtract the radius of the Earth from that, again, 6.38, second e to the 6, I get a very similar number, 3.59 times 10 to the 7 meters. So again, we get numbers, and again, they're slightly different based on the values we decide to use for the mass of the Earth. However, they're right on the same scale. You get the correct answer. You get full credit either way.